So we have this our second speaker, Ruben Van Belle, who's going to talk about the algebras of the Giry monad. Okay, go ahead.
Yes, thank you. Yeah, okay. So I'm going to talk about the algebras of the Giry monad, which is a probability monad. So we do know a lot about the Gleisli category of the Giry monad because it's a Markov category. But the category of algebras is a bit more tricky. For other probability monads, like the distribution monad and the Radon monad, there are nice descriptions of what the algebras look like, but for the Giry monad, it's a bit more difficult. So the goal is to obtain a classification of these algebras, or at least a presentation of what they look like, and then give some properties. So we will almost get there. So I will give sort of a nice presentation, a topological presentation of a certain class of algebras of the Giry monad. Okay, so this is the plan. So I'm first going to just quickly remind you what the Giry monad actually was. Then I'm going to give some examples of what these algebras look like and algebras of other probability monads to give some intuition of what we're looking for. And then this section 3 is going to be the main thing. So we're going to topologize Giry algebras and then using some topological properties, hopefully, yeah, or well, we will say some interesting things about the structure of these Giry algebras. Then I might say something about this. So we can also put an order structure on these Giry algebras to get some more information, but I might skip this section. And then I will end with an application on random variables that take values in an algebra of a Giry monad. And yeah, from now on, I will just say Giry algebra to mean an algebra of the Giry monad. Okay, so what was the Giry monad? So the Giry monad is a monad on the category of measurable spaces, which I'll denote by meuble. The endofunctor sends a measurable space omega to the space of all probability measures, and the sigma algebra is generated by all these evaluation maps. So for a measurable subset, we can send every probability measure to P of A. So that's what it does on objects. On morphisms, we send a measurable map F to the measurable map that pushes forward a probability measure on omega 1 to the probability measure on omega 2, so pushing forward along F. And that gives us a functor, which we'll call G. Okay, then the monad structure. So a multiplication can be given in the following way. So if we have a probability measure on the space of probability measure, which is here bold P, then we can send that to a probability measure just on omega by sort of integrating away one layer of probability. So that's given by this formula. So yeah, what this really is doing is it's integrating this map with respect to bold P. And that gives us a natural transformation. We also have a unit by sending every little omega to the direct delta omega, which is the probability measure that is completely concentrated on this element omega. And okay, that gives us another natural transformation, giving us a monad, which is a Giry monad. Okay, but now we want to sort of investigate the algebras of this monad. So I'm going to look at some examples of algebras of this monad and algebras of some other probability monads to get some inspiration of what a general classification would look like. So the intuition in general is that the structure map of an algebra of the Giry monad is an expectation operator or a barycenter operator, something like that. So it's a very convex space. And one of the main examples, so the Giry algebras sort of come in two flavors. The main example of the first one is going to be this. So if we have the interval 0, 1, then we can define a structure map by sending a probability measure to the integral of the identity function with respect to P, so the expectation. and that satisfies the algebra structure. So if we integrate with respect to a Dirac delta, that's just going to give us these elements that it measure is concentrated on. We also have, yeah, now this holds by the usual thing by approximating our identity function with simple functions, and then the definition of mu sort of gives us this. So okay, this is the one of the main examples of a Giry algebra. Then sort of the other flavor of Giry algebras is usually of this form, this more combinatorial kind of situation. So the main example for that I have is the set 0 and infinity, or just two-element sets, which sends the probability measure to infinity the moment there's some probability mass, some positive probability mass on infinity, and not it's only going to send it to 0 when all probability mass is concentrated on 0. And this satisfies the unit laws of an algebra. Then to see that it satisfies the other algebra structure, or yeah, it satisfies the other axioms of an algebra structure. We look at a measure P on the space of probability measures on two-element sets, and we know that the preimage of 0 is just delta 0. That gives us these equivalences. And then because by definition, we really only have to look at what's happening on if we evaluate our probability measure in 0, then well, that gives us this, and then you can check that. Yeah, this is enough to verify that it's an algebra. Okay, then other examples, other kind of intervals and products of those, other kinds of lattices. These all are examples of Giry algebras. Okay, then for other probability monads. So we can look at distribution monads, which is similar to the Giry monad, but it's only finitely supported probability measures, and it's on sets. And the algebras of those are convex spaces. So these are abstract convex spaces, as for example described by Tobias Fritz in here, which are which is a set together with a family of operations indexed by lambda, so taking convex combinations using satisfying certain commutative diagrams. And examples of those are the real line vector spaces, lattices. So yeah, every Giry algebra is a convex space, but not the other way around. For example, the real line is a convex space, but it's not a Giry algebra. Then another example of a probability monad is the Radon monad. So this is a monad on compact Hausdorff spaces, and it's looking at the Radon probability measures. And the algebras of these are also described as convex compact Hausdorff spaces, which is compact convex subsets of locally convex topological vector spaces. Where the structure map then is given by sending a Radon measure to its barycenter, but whatever that is. And that requires some functional analysis to prove that this exists and that is all working well. And yeah, our presentation of Giry algebras is going to be in a similar style as this. Okay, then for the main thing, we're going to topologize our Giry algebras to say something interesting about the structure of the algebra. But before we look at the actual topology part, I'm going to look at some associated vector spaces to first convex spaces and then Giry algebras. So first I'm going to associate a vector space to convex spaces. So if we have an algebra of the distribution monad, which is a convex space, then we can look at the vector space of finite signed measures, C, which we'll call MC. And then we can look at this subspace. So it's a vector space generated by these P minus delta gamma P. So identifying finitely supported probability measures with its convex combination, really. Um, we can look at this subspace, and then we can quotient out MC by this subspace, which we'll call V1C. And this will give us a left adjoint to this forgetful functor. So every vector space is a convex space. And then every convex space can be turned into a vector space in a universal way by this construction. Okay, but this looks a bit messy maybe, so we can formulate this slightly more categorical. So we can look at this co-equalizer. So this is the kind of co-equalizer you expect in something that has to do about algebras of a monad maybe. But okay, so why is this working? So these finite sums, we can rewrite them as in terms of mu in the following way, where Q is then this probability measure on the space of probability measures. And then, using that, we can see that the previous construction is exactly this co-equalizer. Okay, so what's the reason why I'm interested in this, and how is it associated to our original convex space? Well, we already know there's a canonical map like this because there's an adjunction, and what it's precisely doing is it's sending an element C to the equivalence class generated by this delta C. And we're going to be interested in the case when this phi1 is going to be an injection. So okay, if we have a convex space, then the following are equivalents. So phi is an injection if we have this cancellation property, if and only if we have this cancellation property. So if we have lambda A plus lambda bar C is lambda B plus lambda bar C, then we can cancel the C. So that means A is equal to B. And this equivalence is due to Stone. But there's another way to formulate this in which is going to be interesting for the rest of the talk. And that's, we can say that this is also equivalent to saying that convex morphisms separate points. So that means, for different points A and B, we can find a morphism, a convex morphism F that takes different values on A and B. Okay, and well, this is usually called just the cancellation property of a convex space, but I'll call this in this talk the first cancellation property C1 because I'm going to introduce a second one, as you probably would have guessed. Okay, now back to the actual Giry algebras. So we're also going to associate vector space to the Giry algebras, and one with even a bit more structure, namely that of a locally convex topological vector space. So okay, we start with a Giry algebra, and again we look at the vector space of finite signed measures on A. Then our first guess of what the vector space that we associate with A would be this, just as analog of the previous example for the distribution monad. So okay, that's a good start. So we can take this co-equalizer, and we can also give just a direct construction of what that would look like. So it looks like this quotient where we quotient out by the vector space generated by this. Well, it's already a vector space, just these elements. So we don't have a formulation in terms of finite sums anymore because we're working with general measures and not finitely supported ones anymore. So this is really just the way to formulate it. Okay, so that gives us a vector space, but I told you we want this to be a locally convex topological vector space. So we will give this a locally convex structure in the following way. For every algebra morphism from A to 0, 1, we can define a semi-norm from V2 to R by sending an equivalence class of signed measures to this integral, which is well defined because F is an algebra morphism, so that's why this works. And it's not too difficult to see that this is a semi-norm just by the usual integral properties. Okay, so this gives us, this family of semi-norms induces a locally convex structure by looking at the topology induced, the smallest topology that makes all these semi-norms continuous. Now the problem is this locally convex topological vector space might not be Hausdorff, and that is something subtle, but it's quite annoying because in usual standards functional analysis textbooks or papers or whatever, usually in the introduction they say, oh, and we assume every topological vector space is Hausdorff. So it's a bit tricky to work with these non-Hausdorff ones. So to get around that, the thing to do is to look at the Hausdorffification of our vector space, which we'll call V3. And this is the quotient map. Yeah, phi 2, 3 is the quotient map corresponding with this Hausdorffification. And we can give an actual construction of this V3. So it's again a quotient where we quotient out by this time this vector space. So all the mu's where mu f is 0 for all f. And again, this becomes a locally convex space in the same way by the same maps really, and it's still well defined so that's all working. So to sort of summarize this, we have if we have an algebra, we can associate a locally convex topological vector space with it, which might not be Hausdorff, but then we can also look at the Hausdorffification of that. Okay, and then again we have canonical maps in a similar style as before, sending A to the equivalence class generated by or represented by delta A, and we are interested in the case where phi is injective, which is going to be precisely when the algebra morphisms separate points, and which is also going to be equivalent to saying that this quotient map is isomorphism, so the V2 was already Hausdorff to begin with, and that A satisfies the C1 property. So this property is strictly stronger than C1, and we'll call this the second cancellation property, C2. Okay, so and this is again to summarize everything relates. Okay, so that means we have inclusion functors. So every C2 is C1 is just an algebra, and we have left adjoints. And these adjunctions are, well, the units are given by these phi1 and these phi3. So the construction really is, we look at the image of our algebra under phi1 or phi3, which is then going to be C1 or C2 because it's a sub sets, which is an injection. Okay, so this, because V3 is a topological space, phi3 of A inherits the topology. In the particular case, when A satisfies the C2, then phi3 of A is where we can identify it with A, so then A becomes topological as well. So we want to study the topological properties of these phi3 of A's, or the A's in the case that it's C2. And the result, and the main result, I guess, is that it's a convex, relatively compact Hausdorff subspace. Okay, I'll briefly go over the proof just to give some kind of idea of justification or why this might true, maybe some intuition. So the idea is we can look at the vector space of finite size measures. This again becomes topological by endowing it with a topology generated by these semi-norms. Now we can take a look at any f, not just the algebra morphisms. And then by this Banach-Alaoglu theorem, we know that this is going to be a compact subset. We also know that this quotient map is continuous, just because how we define the topology here. So that means the image of U, yeah, sorry, this set is called U, is going to be a compact subset of V3. This is also a typo, sorry. And then we can show that phi3 of A is a subset of PU, and therefore it's relatively compact. Also, yeah, it's because V3 is Hausdorff and phi3 is a convex map. It's a convex Hausdorff relatively compact subset. So that tells us something about the topological properties of the objects. Now we are going to look at topological properties of these algebra morphisms. So we can factorize an algebra morphism in the following way through this phi3. And then the result is that an algebra morphism is equivalent to saying that this one is continuous and convex. Yeah, a quick proof for this is we can, if we have a probability measure, then we can approximate it by a net of finitely supported ones, and then by these equalities, we can show that if our f tilde is continuous and it's convex, then yeah, we get that f is an algebra morphism. Okay, then a corollary. So in the case that a V3 is finite dimensional, we can say some interesting things. Namely that sort of everything reduces to maybe just a convex spaces case. I'll start with the second one. So every convex map is an algebra morphism. So that follows from the previous result really, because in the previous result we said convex plus continuity implies algebra morphism. So that means in the case of finite dimensional, that we're working with finite dimensional vector spaces, we get the continuity for free. So convex maps become algebra morphisms. And therefore, if convex maps separate points, algebra morphisms also separate points, which gives us the first property. That C1 is equivalent to C2. Okay, then I think the final theorem in this part is to give an actual description in terms of functional analysis of this abstract structure map alpha. So alpha of P under our phi3, so in the vector space, is this Pettis integral of the map phi3. So this is some kind of integral in functional analysis. So that sort of, yeah, formalizes the intuition that alpha is some kind of integration operation. So we can describe it as an actual integral. The reason why this is true, because phi3a is convex, relatively compact, and so on. We know that this integral exists because the domain is sort of compact enough. And then if you have a linear continuous functional like this, then this is an algebra morphism, again, because of the previous result that algebra morphisms are continuous and convex, which means that we can swap the alpha with here just the usual Lebesgue integral. And this is the defining property of this Pettis integration. Okay, then we can formulate this all a bit more categorical in the following way. So there's an adjunction between Giry algebras and Radon algebras. So we can send the Radon algebra to measurable space with a certain sigma algebra generated by these continuous convex maps. And then using Pettis integration, we can again define a structure map which is extending the structure map of the Radon algebra. So we can sort of say something about all probability measures, not only the Radon ones. And that gives us a full and faithful functor from Radon algebras to Giry algebras. Now, using the previous constructions, we can also define a functor in the other direction. So if we have an algebra, a Giry algebra, then we can look at this image closed. This is going to be a Radon algebra because it's compact, it's Hausdorff, it's convex, and the Bayer-Sindre operation is precisely going to coincide with this integration, this Bettis integration of this phi tree. So that means every Giry algebra induces a Radon algebra. And these form a pair of adjunctions. Well, these form a pair of adjoint functors. And the core unit is an isomorphism if and only if A is C2. Okay, but we can say even a bit more about this adjunction. So we can decompose this adjunction through this category of rel comp cov, so relatively compact convex Hausdorff subsets of locally convex topological vector spaces. In the following way, so yeah, here we just do the process in two steps. So first, if you have an algebra, we can first take the image under phi and then take the closure. So that's the way how it decomposes. For the first adjunction, we have that the core unit is always a natural isomorphism, and the unit is an isomorphism if and only if A satisfies C2. And that then gives us the sort of conclusion of this section that the category of the category of algebras that satisfy this C2 property are precisely the relatively compact convex subsets of these topological vector spaces. Okay, I'm not going to say too much about this, but I'll maybe just show you this slide. And the reason why I'm interested in this, because this is also a bit more like a work in progress. But we can also give an order to the Giry algebras. In the following way, we can say that A is smaller than B if every convex combination from A and B always lands in B for lambda not equal to 0. And that happens when we have these situations when there's an infinity involved in our algebra. And this forms a partial order. So we have a functor again from algebras to partial orders. And the main reason why I'm interested in this is because we already have some sort of nice topological description of the ones that satisfy C2. But the question is now, what if they don't satisfy the C2? And that's precisely the case when this order is going to be interesting. So if A satisfies C2, then PA is going to be a discrete order. So there's nothing really interesting happening. But so if there's something interesting happening, then we know it's not C2. So this sort of would say something about the other type of Giry algebras that are of a more combinatorial flavor. So yeah, then we can define infinite elements, and I'm going to skip this part, but I'm going to finish with this sort of application of algebras, of random variables that take values in Giry algebras. So yeah, the reason why I'm interested in this is because I think that Giry algebras are sort of the correct codomains of random variables, because what you want to do with random variables is to integrate them, look at expectations in all kinds of form. And the algebra structure of a Giry algebra allows you to do that. Okay, so I'm going to say something about conditional expectation of these kind of random variables. So a Giry algebra random variable is a measurable map from omega to our fixed Giry algebra A. Then we can define expectation in the following way. Which is justified by this example. So if we look at this example of a Giry algebra, then our definition precisely coincides with the usual expectation, which is good. Okay, then we can also look at conditional expectation in the following way. So if we have a random variable taking values in A, then a conditional expectation of f with respect to a subalgebra G or a sub-sigma algebra. So it's a sigma algebra is a G measurable random variable taking values in A such that the following is satisfied. And this coincides precisely with the usual definition if A is 0, 1 or 0, infinity. But because now we have nice topological properties or because we have topologized our Giry algebra and associated with like a topological vector space, we can use some functional analysis. So we can look at the case where V3 satisfies this Radon-Nikodym property, which is a property people in functional analysis talk about. And if that's the case, then we can guarantee that exists an almost surely unique conditional expectation of a random variable with respect to a sub-sigma algebra or even more general with respect to maybe a measure preserving map or something. Yeah, and that's where I'm going to finish.
All right. Thank you. That's a very nice talk. All right. Are there any questions or comments for Ruben's talk? Maybe in the meantime, I have one. So your algebra, let's say that the C2 one, with the property C2, which algebras are included in there? For example, are all free algebras satisfying C2?
Yes.
Okay. And do you know if they're closed under taking, I don't know, products or maybe colimits, coequalizers?
That's a bit more tricky. So I don't have a good answer for that, but so that's maybe why this description or presentation of these C2 algebras in this form is can be interesting because maybe if you think of it in terms of this category, it's more it's easier to think what's the co-limits would look like because maybe there's some kind of closure operation that you need to perform to get co-limits and things like that.
Well, we definitely don't expect all colimits to be there because then every algebra is a colimit of free ones. But maybe some nice colimits that are co-product.
I see. Yeah.
I see. Thank you.